This presentation is about my paper and thesis concerning a computational model for the second-order adaptive causal relationships between anxiety, stress, and physical exercise. To introduce the topic, we first have to get an idea of the scope and the problem. The problem of stress and anxiety is highly common and affects a broad portion of the population with at least mild symptoms. Studies have shown that the prevalence of anxiety symptoms in the general population is at around 32%, and that even mild symptoms should not be left untreated. Even mild symptoms untreated can result in a heightened risk for them to progress to a clinical severity. And therefore, physical exercise seems to be a promising, easy, and accessible treatment option, given its anxiety-reducing properties. This is especially true in the current times of closed sports clubs and gyms. But to be able to understand the effects of physical exercise on anxiety, we first have to understand the disorder itself. For this, different approaches exist. The classical approach considers the symptoms to arise from or to be caused by the underlying disorder. The network-oriented approach, on the other hand, considers the disorder to be the emergent behavior of a dynamically interacting network of distinct symptoms and predispositions. Having understood this, it is possible for us to create a network model depicting the underlying mechanisms of physical exercise's reduction of anxiety. The goal in this is to examine the underlying effects and causal relations in more detail to visualize them. Further, a created network model like that also enables us to simulate effects of different exercise frequencies, so different levels of treatments. For this, I conducted a literature review to get the current understanding of this problem. I found that physical exercise has a proven significant but small anxiety-reducing effect, but that this anxiety-reducing effect is dependent on the intensity of the physical exercise. There are different studies stating slightly different timeframes in which the anxiety-reducing effect begins, but all of them conclude that at around 30 minutes, the effect started and is at its top. Therefore, a moderate intensity exercise of 30 minutes shows the best results. Moderate intensity is important here because we have to stay below the ventilatory threshold, which is the threshold at which the breathing and exercise becomes unproportional to the actual exercising. Basically, to make it easier to understand, we need to stay at a comfortable pace of exercise for the anxiety-reducing effect to be the biggest. It was also found that stress and anxiety have a direct positive correlation. So if we are more stressed, of course, we are also more anxietic. Physical exercise also has a positive effect on one's stress response. So through this effect, there's also an indirect correlation through the direct positive correlation to the anxiety. So if physical exercise not only reduces anxiety directly, but also reduces stress, it has an indirect effect on anxiety furthermore. Also, it was found that physically active individuals have a higher threshold for the activation of their biological stress response, which is the HPA-axis activation. It is further found that physical exercise also releases certain neurotransmitters and neurotrophins in the brain. After a certain time, normally 15 minutes, the first neurotransmitters are transmitted, and they have three different main effects. A group of them will increase the neurogenesis, another one the angiogenesis, and also the neuroplasticity is increased. In this, especially BDNF, the brain-derived neurotrophic factors are important. Exercise also induces the release of own body opioids and cannabinoids that have a direct anxiolytic effect, so a direct anxiety reducing effect. Further, the increase of neurotrophins leads to a further increased neurogenesis. This further increased neurogenesis, but also the increased neuroplasticity, is important in the stress and anxiety regulation, especially in the emotion regulation, given that a higher plasticity leads to a higher adaptivity of emotional and behavioral control networks. For example, in the case of the stress response, it would be the ventral medial prefrontal cortex. And this high adaptivity leads to a better ability to respond to anxiety and stress, or in general to a better emotional response. To model this, we will make use of adaptive computational network models. Adaptive computational network models aim to represent complex temporal causal interrelations of real-world phenomena. The model should help to visualize direct, indirect, and indirect causations and enable simulations with differing external factors. These models are defined by the following characteristic of its nodes and states: the connections between two nodes, which represent real-world causal relations in the network structure, their weight of those connections, which demonstrates the strength or the importance of these connections, and the timing. The timing is determined by the speed factor. It can be understood as the rate of change of a node. So if it's fast to change or if it's slow to react to outside influences. Also, an important factor are the aggregation functions. With them, we determine how multiple inputs are combined, although there are also some combination functions that will just relay the full input if, for example, there's only one input per node. It's also important that we understand how adaptivity is modeled through these in these adaptive computational network models. We do this through higher order self-models. They usually consist of self-model replication states and enable us to model adaptivity and reactivity of weights, speed factors, networks characteristics, for example, the parameters of the combination function. We are able to, instead of using fixed values, just a reference to another node, which then translates to the adaptivity. Based on the literature review and on an already existing stress emotion control model, I created a further expanded model consisting of both the physical exercise effects, anxiety, and the stress regulation. The base level states aim to represent the direct and indirect relations between the different interconnected real-world phenomena of the stress and anxiety response, as well as the effect of physical exercise on it. The states in the first verification level represent the principle of Hebbian learning for two connections at the base level, while the states in the second verification level express metaplasticity, namely the persistence of what is learned and the speed of learning. Besides that, the first verification level also models the adaptive threshold parameter of the biological stress response. And to have the desired effects and relations, we use a range of different functions in this model. The first that we use is the identity combination function. It accepts the full input if there's only one incoming connection. The second that we use is the advanced logistic sum function. It is often used if we have to combine a number of different inputs, and it has the steepness and threshold as parameters that can be adjusted. We also use the Hebbian learning combination function, of course, in the both states that show the connection between the control and feeding state. Also, two further custom input functions were added. One that shows and simulates the input of the stressor, and one that inputs the physical exercise. One benefit of the allogistic function is that it's able to model a biological threshold surpassing. If we have a high steepness, the surpassing of the threshold leads to a stark and sudden increase in the combined value. So therefore, we are able to create this effect of biological threshold that is surpassed and therefore activated. To get our results, we will run a simulation. The simulation will be conducted for several reasons: to explore the claim of a reductive effect of physical exercise, and to also be able to depict different scenarios of different levels of physical activity integration into the individual's life. The simulation will represent a normal waking time of a person, so from 8 to 22. Each time point will equal 5 minutes, so we have a total of 504 steps. The stressor will be apparent from 12:30 until 13:30 in each scenario. So at noon, we always have a stressor apparent on each of the 3 days. In scenario 2, we add one physical exercise in the morning. In scenario 3, we also add a further exercise in the afternoon. These are the results of the first scenario. We can see that without any outside stimulation, for example, through physical exercise, the stress level and the anxiety level stay high and nearly the same throughout the experiment and simulation. We can, however, see that there is this increase when the stressor is apparent, although it is only small. We can further observe that there's a constant decrease in the persistence factor. So the learning is virtually blocked. In scenario 2, where we have one physical exercise in the morning, we can observe that stress and anxiety actually reduce throughout the simulation, although only slightly. We can see that the physical exercise induces the release of neurotrophic factors and opioids and cannabinoids. And the opioids and cannabinoids have a direct anxiolytic effect, which can be observed in the reducing of anxiety at those times. But the neurotrophic factors also increase the learning speed. This, through indirect relations, will in the end result in a faster and strengthened connection between the feeling and control states, which increases the ability of emotional regulation, which therefore enables the individual to better cope and reduce their anxiety and stress. In scenario 3, we see that the effect of the reduction in anxiety and stress is even stronger, and that accumulation effects lead to this. So what can we conclude? Mental disorders are more and more seen as emergent behavior of dynamically interacting networks of distinct symptoms. We could show that the model successfully showed the emergent behavior that were found in the empirical literature, so its validity can be considered as confirmed. The created model offers the possibility of simulating different treatments and additionally offers the basis to develop a virtual agent model of a patient. Further, like the research already showed, the simulation again confirmed that physical exercise has a positive influence on anxiety, has a reducing influence on anxiety levels, and that should therefore be promoted as a treatment, as an easy and accessible treatment. But no research is without limitations, or no research should just be seen as something already finished. We should always also look in the future. The limitations of the model are quite clear. The relations were only depicted on a macroscopic level, so a more advanced level should also incorporate the underlying mechanisms of the emotion regulation and biological stress response in a greater detail. For this, a combination with additional computational models in this domain could be useful. If we combine enough, we might be able to create a holistic representation of the complex biological and neurological interdependencies of physical disorders. Further, we should also keep in mind that a statistical significant testing of the results would have been to preferred. Further research may focus on the creation of a generalized model, representing typical neurological and biological symptoms of serotonin and dopamine availability impacting disorders. This would not only enable us to compare different models better, but also would broaden simulation possibilities and reduce the creation time of simulations. These are the references used. Yeah, other questions or the discussion?